Well, good evening, everybody. Thank you to Larry for the introduction and for inviting me to speak to your society, and thank you all for coming out tonight. So I am an astronomer. As you'll see, I'm a little bit of a different type of astronomer than what you're used to, and I have had enormous fun over many years now trying to figure out these very strange objects called fast radio bursts. So normally when you think of a telescope, many of you probably own a telescope and you're pretty sure what a telescope looks like. And of course, if you're a professional astronomer, then your telescope might look something like this. This is the Gemini Observatory, which is, I think, about a mirror that's about 6 meters across. And if you're really lucky, your telescope looks like this. This is, of course, the James Webb Space Telescope, many millions of miles from here, which is transforming our understanding of the universe. And although these two telescopes look different from each other, and indeed probably different from the telescopes you have at home unless you have a lot of money, they're both similar to each other and to your telescopes, in that they work in the optical part of the spectrum, the same part of the spectrum that your eyes work in. Where's my pointer? Right there. So they are collecting light in this part of the spectrum, the part of the spectrum that we can see and which we see when we look up at the night sky. Now, of course, that's only a tiny sliver of the spectrum, and modern astronomy uses all of these different types of light, starting from the most energetic types of light, gamma rays, and all the way down to the other end. So you've heard of all of these terms, gamma ray and ultraviolet and microwave and so on. And different objects produce all of these different types of light. There's nothing intrinsically different about gamma rays versus infrared versus visible light. They're just different types of light, and it just turns out that our eyes are only sensitive to one particular type of light. So the type of light that I study are radio waves. So we're all very familiar with radio waves. Those are what transmit the signals through the air that allow us to talk on our cell phones and listen to the radio, and perhaps, not so much anymore, but in the old days, that's how you would receive your television signals as well. And it turns out that there are objects, different types of objects from the ones that you see with your eye, that are all over the universe and are producing radio light. And if you have a radio telescope, then you can see those objects. So radio telescopes, of course, look quite different from optical telescopes because a different energy of light requires a different type of technology to collect it and to focus it. So rather than having a big mirror and a big tube, radio telescopes look like this. They look like big dishes. So here is one of the larger radio telescopes in the world. This is a telescope that's about more than 300 feet across in Greenbank, West Virginia. And here is a very famous one. This is the one that transmitted the moon landing. This is the Parkes radio dish in Australia, and it's about 200 feet across. And so the wavelengths of radio waves are much longer than the wavelengths of visual light, and then so the telescopes have to be correspondingly larger. So if you could somehow put on your radio goggles or your radio antennas and you looked up at the sky, what would it look like? So here is what the whole sky looks like in visual light if there was no annoying Earth horizon or clouds or anything else. This is the entire sky, so you can never get this view at once from Earth. But of course, here is the Milky Way right through the middle with all various features. Here are the small Magellanic Cloud and the large Magellanic Cloud. There is Andromeda and various other features that you're probably familiar with. So roughly speaking, sort of this half here is the northern sky that you can see from up here, and this half here is the southern sky that you can only see from down under. So if we now put on our radio goggles, this is what the sky looks like in radio waves. And some things are the same and some things are different. All the stars disappear. There are very few stars that you can easily see, but the Milky Way is still there. So this big stripe through the middle, this is false color. This is not real colors, but red is sort of bright and blue is faint. You can see that the Milky Way is still this very dominant structure that runs right through the middle, but pretty much everything, almost everything else, Sorry. Almost everything else is different. So what else, if you zoom in on these patches aren't blank, but there's lots of things that you can see if you zoom in on these patches if you've got good radio vision. And there are lots of other things in the radio sky besides the Milky Way. The two main things that you see in the radio sky besides the Milky Way are black holes and neutron stars. So you all know what a black hole is. It's this big sort of giant cosmic incinerator that's sucking everything in around it. And you might know that you can't see black holes because they suck in even light, and that's why they're called black. So how could you see one? Well, we can't see the black hole itself, but we can see its effect on its surroundings. So as material swirls into the black hole, some of it falls into the black hole and disappears, but some of it just misses, a bit like a bad snooker player who just misses the pocket and it sort of bounces away at high speed. Some of the material just misses and gets shot out away from the black hole at extremely high speeds. So that's what you're seeing here. The black hole is right in the middle there. You can't see the black hole itself, but that bright dot is all the material swirling into the black hole, and you can actually see the material being shot out in two opposite directions in these very narrow jets. This is a distance of millions of light years, and eventually the stuff slams into its surroundings and sort of all piles up over here and here. So this is an effect over millions of light years of a black hole trying to suck in its material around it, but actually blasting it off into space. And so some of the brightest objects that we see in the radio sky are actually black holes. The things that you think should be the darkest things in the universe are actually some of the brightest things in the universe. And then the other things we see are these neutron stars, or pulsars. These are very strange objects. They're collapsed stars that are only sort of about 10 miles, 15 miles across, and they spin very rapidly. And for reasons that we still don't entirely understand, they produce powerful beams of radio emission along their two poles. And so as they spin, you get this lighthouse effect. We never see a picture like this. I wish we could see a picture like this. But what we do is what we do see is that effectively that little plot on the bottom, we just see an object that is winking on and off with a very regular period. These are some of the most stable clocks in the universe, more stable than some of the best clocks we have here on Earth. And we can deduce exactly how fast these stars are rotating by the time it takes to see one pulse and then the next pulse. So the black holes on the left are relatively steady objects, and the pulsars, the neutron stars, are objects that are not steady. They're constantly flashing on and off. But those are two of the main things that we see when we look with our radio telescopes. And both of these types of objects were discovered in the 1960s, and throughout the last 50 or 60 years, we have been building bigger and bigger radio telescopes to study different types of black holes and different types of neutron stars. So in July of the year 2001, so that's quite a long time ago now, almost 25 years ago, astronomers were using that telescope in Parkes, Australia, the one that was also used for the moon landing. They were using it to search for those spinning neutron stars in one of the nearest galaxies to our own, a little runt of a galaxy. It's not a very big galaxy, called the Small Magellanic Cloud. You can just see it with your naked eye from the southern hemisphere. It looks like a little cloud in the sky, hence its name, the Small Magellanic Cloud, or the SMC. Not very impressive to the naked eye. Not super impressive with a telescope either, but this is the Small Magellanic Cloud. And they were looking for these spinning neutron stars in the Small Magellanic Cloud. And they found a few, and that was nice, and they moved on and forgot about it. About 6 or 7 years later, someone realized that there are better ways to process the data. And they said, well, maybe if we go back and process the data again, maybe we'll find some more of these spinning neutron stars. Technology always improves. People had kept the data, they hadn't thrown it away. And so you could play back the data through your computer again and process it in a different way, and maybe you would find something different. And, well, they didn't find any more pulsars, any more of these spinning neutron stars, but they did find something rather unexpected. And so at this particular position here, which you can see is not really in the galaxy, this is sort of where you'd expect to find those spinning neutron stars. But the telescope sort of just did a grid, and it did observe some positions that were a little bit off the galaxy. But at that position there, they found something somewhat unexpected. And so the signal hit the telescope on July the 24th, 2001, but no one noticed this signal hiding in the data until they reprocessed the data in about 2007. And what they saw was something like this. So let me explain what this is. This is a graph, and on this graph, on the x-axis you have time in milliseconds, so thousandths of a second. So 1,000 milliseconds is 1 second after they started recording. This is 1.5 seconds after they started recording. And in this axis, we have the frequency of the radio waves. So normally when we measure the color of a radio wave, we don't say that it's red or it's blue. We measure it by its frequency. But the difference between a red light and blue light is the frequency of the light. And for radio waves, the frequencies tends to be things like megahertz. If you listen to FM radio, you're very familiar with megahertz. Your favorite radio station might be 101.3 or 96.2 or whatever. So you can see these ones are a little bit higher. The FM band is sort of in the 90s and hundreds of megahertz. This is about 10 times higher. So we're 1,300 megahertz, 1,400 megahertz, 1,500 megahertz. So at every millisecond, at every frequency, the telescope is recording how bright the signal is. And so if you start, say, at this point here at 500 milliseconds after they recorded the data, and if you just sort of work your way across the band, you can see that there's a bit of junk here and a bit of junk here. So that's like someone transmitting, maybe a radio station or something. But the rest of it just is static. There's nothing happening at this particular time. But you can see something starts to happen here. At about 700 or 800 milliseconds after they started recording, there's a very bright signal coming in. But it's only bright at 1,500 megahertz. If you wait a little bit longer, there's a bright signal that comes in at a lower frequency. And if you wait longer again, there's a signal coming in at an even lower frequency, and so on and so on. So there's some sort of really bright signal that's happened, but it arrives at the telescope at different times depending on what frequency it is. At 1,500 megahertz, the signal will arise relatively early, but there's a delay of about 300 milliseconds, or about 0.3 of a second, where this really bright signal arrives at the bottom of the frequency band that's being covered. And then you can see after that, there's just nothing again. Normally signals in radio astronomy are steady, they're on all the time, or they're like one of these spinning neutron stars, they're on, off, on, off, on, off. And this one you can see is quite different. There's nothing, and then it's on, and then it's gone again. And people have looked back at this exact position many, many times, and they have never seen anything ever again. So this is a bit odd, a really sudden, bright flash of radio waves that was never seen again. And the other thing that's odd is, as you're seeing, you would think that maybe the signal should just arrive at every frequency at the same time. That is, that this white stripe should be a vertical line, but you can quite clearly see that this line is bent. The high frequencies arrive first, and the low frequencies arrive later. So this particular situation where the different frequencies arrive at different times, this is something that we have seen before. It's the same thing that we see for neutron stars living in our Milky Way galaxy. And it's due to an effect called dispersion. And what dispersion is that space isn't really empty. Space is quite a silly name for it because it's not space. It's got stuff in it that, they should call it stuff. And space has gas in it. It's a very low density gas. It's billions and billions of times weaker, less dense than the air in this room. In fact, the air in space the gas in space is more rarefied than the best vacuum that we can make on Earth. So if you went over to some random place in space and tried to say, is there anything here? By our standards, we would say, no, it's a vacuum. But it's not. There is gas in space. And it turns out that what we call the speed of light, 186,000 miles a second, that's the speed of light in a vacuum. And if you're not in a vacuum, then light travels a little bit slower than that. What's more, if you're in a vacuum, then every color of light travels at exactly the same speed. It doesn't matter whether you're red light or blue light or radio waves or X-rays, everything travels at exactly the speed of light. But what dispersion is that if you are not in a vacuum, then not only does light travel a little bit slower than the speed of light, but different colors travel at different speeds. Short wavelength light, high frequency light, energetic light travels faster than low energy light. So for visual light, when the light is traveling through space, blue light actually travels just a tiny bit faster than red light. And so that's exactly what is happening here. So as you can see in this, in this animation, let's get it going again. In this animation, so we're in a perfect vacuum, and you can see all these different types of light are traveling at the same speed, but then you go through a cloud of gas, here we go, and you can see that now the short wavelength light, the high frequency light pulls ahead and arrives first. And so therefore, you get this pattern like this. Whenever you see that pattern where the high frequency light has traveled, arrives first, that tells you that the signal you're detecting is not coming from, say, just above the Earth, but it's traveled a long way through interstellar space. And so here's sort of another graph just showing you, this is just sort of a typical object. This isn't the one that I'm talking about now, but we see these plots all the time. The high frequencies arrive first and the low frequencies arrive last. In this case, you can see the delay is a lot longer. It's about 0.9 of a second. And so not only does this tell you that this signal has to have come from interstellar space, but it can actually tell you how far away it's traveled. Because the longer distance it travels through space, the further ahead the high frequency light is going to get ahead of the low frequency light. If you are running a race around a track with a fast person and a slow person, if it's just a 100-meter dash, then the fast person might win by this much. But if it's 10 laps around the track, then the faster person's going to win by much, much more. And so essentially, the longer that delay, it tells you the farther the light has traveled. And so that delay essentially tells you how far away this object has come. Another way of visualizing is you can actually turn this into sound. We turn radio waves into sound all the time. Every time you talk on your mobile phone, you are taking a radio signal and converting it to sound. So this is not as artistic or as speculative as it sounds. It's quite normal to turn radio waves into sound. So imagine you were listening with your headphones in 2001 as the signal came in. It would sound something like this. So just static. Whoops, let me play it again. Just static, and then. So that descending tone is what happens when you have a very bright burst, but different parts of it arrive at different times. All right, so does that all make sense to everybody, this dispersion effect? So you can work out, based on how long it takes from the high frequency to low frequencies, you can work out how far away these objects are. And so this has been known about for a long time. And if it was an object in our own Milky Way, you might get an answer like that it was 5,000 light years away. That's sort of a typical number for the Milky Way. It's a long way away, 5,000 light years, but it's in our own galaxy. The Small Magellanic Cloud is not in our galaxy. It's the next galaxy over. So if it was in the Small Magellanic Cloud, you would get an answer based on this dispersion that it would be about 170,000 light years away, because we know that that's the distance to the Small Magellanic Cloud. And so, you know, they found this object, and normally when you find objects, they're either it's just something in the foreground, like looking at a speck of dust through the windshield in your car. So when they went to calculate the distance to this object, whatever it was, they expected the answer to be about 5,000 light years, which would mean it's just something in our Milky Way. All these stars that you can see here are just foreground stars in the Milky Way, so maybe it's just some foreground object. Or it's some object that's on the edge of the Small Magellanic Cloud, so it would be 170,000 light years away. So they calculated the distance to it, and the answer they got, so this is like the entire history of the universe on one slide. Here's the Big Bang, and going all the way through to the present day, 13.8 billion years after the Big Bang. And this object, whatever it is, turned out to be 3.5 billion light years away. So by the standards of the entire history of the universe, you know, it's not all the way back here or here or here, but it's big enough that you can actually see the difference on this chart. If I tried to put the Small Magellanic Cloud, which is 170,000 light years on here, it will just be the same as present day. But this thing has been traveling towards us for 3.5 billion years before the signal hit the Parkes radio dish in July of 2001. So to put that in perspective, the Earth is only about 4.5 billion years old. So this signal originated not too long after the Earth was formed, and it's been traveling towards us for the entirety of geological history. So this was a bit of a shock. Firstly, remember this object, the objects we're used to seeing with radio telescopes are either steady or they pulse and repeat regularly. This was neither, it was just a single flash. So that's not normally something that we see. And what's more, its dispersion told us that this object had to be 3.5 billion light years away. This object was very, very bright. It was much, much brighter than the sorts of things we normally see with this telescope. And so not only is it really bright, but it's also really, really far away. If this was just a typical object, the sorts of object that you see in the Milky Way all the time, and you moved it to 3.5 billion light years away, you'd expect this object to be very, very faint. But the fact that it is both really, really bright at the telescope and is 3.5 billion light years away tells you that the power in this object has to have been absolutely enormous. So this object is incredibly powerful. So the sun is a very bright object. We all know not to look at the sun. You can hurt your eyes, and that's because the sun is incredibly luminous. If you were to take all the energy of the sun, and I'm not talking just about the energy that hits the Earth, because that's only one direction from the sun, but all the energy that the sun is emitting in every direction around the sphere, and you stored up that energy. So imagine building a shell of solar cells all around the sun and gathering up all that energy. You would have to gather up that energy for a full year to match the energy that that little flash that lasted for just a fraction of a second gave off. So whatever this object is, it's 3.5 billion light years away, and it gave off more energy in about a millisecond than the sun gives off in a year. So at this point, people are going, this is really weird. It gets weirder. Because this object was only on for a millisecond, so I should back up and say that when you look at the original signal, it looks like it lasted from here, which is 700 milliseconds, to about 1,000 milliseconds. So it looked like it was on for about 300 milliseconds. But that's not true. That is due to this dispersion effect. If you take out this dispersion effect and just measure how long from the start of this pulse to the end, it's about 1 millisecond. So this thing was very, very brief. It was just a tiny little flicker, but was unbelievably bright for that flicker. And that length of the pulse tells you something else. It tells you that whatever this object is that's unbelievably luminous, and 3.5 billion light years away, it also tells you that it had to have been very, very small. So let me explain that to you. So we talked about the speed of light. Light travels at 186,000 miles a second, which is traveling about 7 times around the world in 1 second. If any of you have ever flown to Asia or Australia or Europe, you know that planes take a long time just to move along a little part of the globe. Imagine doing that 7 times in 1 second. Well, that's the speed of light. Okay? So when we see an object in space change, it turns out that that tells you how big the object, a limit on how big the object could be. If you see an object brighten and fade over the course of an hour, it turns out that physically it's not possible for an object to naturally change over the course of an hour if it takes light more than 1 hour to travel from one side of that object to the other side. Is that okay, or do people want me to explain that more? Explain more. Okay, so imagine that I'm in a stadium. Big stadium, big football stadium, 100 yards one into the other. Now, if I am talking maybe with my megaphone, you all know that it takes a second for the sound to travel from the front of the stadium to the back. So what would happen, suppose the whole stadium's full of people, and I'm on my megaphone, and I say, all right, I'm going to count to 3, and on the count of 3, I want everybody to click their fingers. 1, 2, 3. Is everyone going to click their fingers at exactly the same time? No, right? Who's going to click their fingers first? The people near me will click their fingers first, and the people at the back will click their fingers last, because it takes time for the sound to get to them. So it'll be pretty much impossible for everyone to click their fingers at all the same time if they're just following my instructions. And so if you were blindfolded, and I said, just listen to the clicking, I explained to them what's happening, that this is a stadium, and I'm going to tell everyone to click, and I'm going to blindfold you, and just based on how spread out the clicks are, I want you to figure out how big this stadium is, you could do it, right? If the clicks were really spread out, you would know the stadium had to be huge. And if the clicks were all together, you'd know the stadium would be really tiny. Does that make sense? So it's the same here. If you see something that happens quickly, then the object that is essentially turning on and off, whatever's happening, has to be quite small. And if you see an object changing slowly, then the object is probably quite large. Except now, instead of the speed of sound, which is what you would use to calculate the size of the stadium, it's the speed of light. So if I see an object that changes over the period of an hour, that object is probably, it sort of has to be smaller than about a light hour across. Because there's no way an object can change in an hour if it takes 10 hours for light to get from one side of it to the other. Does that make sense now? Is that okay? So, all right, so this object somehow turns itself on and turns itself off again in 1 millisecond. So that means that whatever this object is, it has to be smaller than 1 light millisecond across. It has to be smaller than the distance traveled by light in 1 millisecond. And that's a really small distance. The distance that light travels in 1 millisecond is about 200 miles. That's a lot. But that means that this object, not only is it incredibly powerful and 3.5 billion light years away, you're thinking, well, if this thing's super powerful, it must be huge. Maybe it's some giant galaxy. This object, whatever it is, has to be less than 200 miles across. Has to be smaller, not much bigger than the Bay Area, whatever this object is. So at this point, things are getting really, really weird. This object has to be unbelievably powerful, unbelievably distant. It has to somehow turn off and on again in a millisecond, and it has to be not very big at all. So when they announced this in 2007, they said, we don't know what this is, but this is really, really weird. And of course, when you find a weird thing, people just like to try and explain it away. People said, well, maybe it's just some weird object. There's only one of them in the universe, and we're never going to see it again, so oh well. Other people say, you know, maybe it was just some problem in your data processing or something like that. And so for many years, people just sort of didn't really know what to do with it. We called it the Lorimer burst because it was discovered, the main person who discovered it was an astronomer named Duncan Lorimer. But then, to our surprise, 10 years later, so now in 2013, remember the first one was 2001, 10 years later, people discovered more of these things. So here are some more. This is just a chart of brightness versus time now. We've sort of cut out the frequency axis, but they all do the same thing. They just sort of go up, and they go down again, and then they're never seen again. And some of them are bright, like this one, and some of them are faint. So now we have 5 of them. We're sort of convinced these things are a real thing, and people tried to come up with a good name for them. So we said, well, what do we know about these objects? Well, not much. We know that they're radio objects. We know that it's sort of a burst, and we know that it all happens pretty fast. So let's call them fast radio bursts. So of course that's a bit of a mouthful. So someone said, I know, instead of calling them fast radio bursts, let's call them Furbies. I cannot tell you how relieved I am that that name did not catch on. But now we universally call these objects FRBs. So FRB, fast radio bursts, and here are the first 5. Now, you might not be very impressed. You might think these objects are pretty rare if it took more than 10 years to find 5 of these things. You might think these are sort of 1 in a million objects. But it turns out that they're really, really hard to find. You have to be looking at exactly the right place at exactly the right time. And if you work out how much of the sky a telescope typically covers at any one time, it turns out to be not very much. And so you have to be extraordinarily lucky to find one. And the fact that they were able to find 5 in 10 years actually tells you that if you could somehow look at the whole sky all the time, you would find about 1 of these every minute. So for the whole of human history, for the whole of the Earth's history, while there were dinosaurs walking around doing these things, every minute while T-Rex was walking around looking for its next meal, 1 of these fast radio bursts was flashing somewhere in the sky. And that's been happening for our whole lives, every minute, with thousands of astronomers studying the sky all day, every day, and no one even noticed the first one of these until 2001. So that's pretty amazing. It also makes you wonder what else is happening out there that we still haven't actually found yet. But the rate of these things is extreme. And so once people calculate this rate, some people were saying, come on, there is nothing in the universe that happens every minute. And there's certainly nothing this energetic. Like, these things are incredibly distant, they're incredibly luminous, they're some very exotic, strange thing. There is no way that this is happening every minute. I'm not convinced. I think this is just some sort of data processing error. And one of the reasons why people were worried is because lots of telescopes had been looking for these fast radio bursts. And so we had 5, and all 5 of them were detected with the same telescope, with the Parkes radio telescope. And all the other radio telescopes in the world had detected 0. So people were saying, look, Parkes, I'm not saying there's anything wrong with you, but it's a little bit weird that you keep finding them and we don't. And people started to say, maybe there's something going on at Parkes that is producing something wrong with the data. And so a very smart scientist named Emily Petrov, a colleague of mine, asked the question, maybe these are not actually coming from space. And she had a very simple idea, which is, after we had started to find a few more of these things, she said, let's just look at what time of day. Normally you don't care what time of day something happens. It doesn't really matter if you detect something at 3 a.m. or 10 p.m. That has no astrophysical significance, because an object that's 3.5 billion light years away doesn't know or care what time it's going to be detected at Earth. So normally we don't actually care what time it was detected. But she decided to make a graph of what time they were detected, and something very curious started to happen. So if these things have been happening every minute since the dawn of time, then all things being equal, it shouldn't really matter what time we detect them, right? You've got just as much chance of detecting one of them at 1 a.m. as you do at 1 p.m. But here is a graph showing you in Australian time, where the telescope is, what time they were detected. And you can see none were ever detected in the middle of the night. They start to get detected about 8 a.m. You really start detecting lots of them at 1 p.m. and then it just sort of tails off, and you never detect any after about 9 p.m. And so at this point she went, uh-oh. And then she said, well, let's try something else. Let's look at the distribution of times of day during the summer, and let's look at the times during the winter and see if they're the same. And it turned out that when you made a graph of the summer ones and the summer ones are all, this graph showing you sort of peak was there for both summer and winter, but for summer it was shifted to the right by exactly 1 hour, which is of course the difference between daylight savings time and normal time. So at this point she's going, oh dear, everyone's going to hate me because I think I have shown these things are not real. And then she said, all right, well, if they're not real, what are they? And it turned out, all right, so when you heat your dinner up in the microwave, you set the timer for what? I'm a 90 seconds guy, but what are you? How long do you heat your dinner up for? You 90 seconds? Good choice. Anyone other numbers? 4 minutes. Oh, wow. You need to buy yourself a new microwave. Anyone else? Anyone going really short with their dinners? 30 seconds. 30 seconds. All right, Larry, you like to live dangerously. So, of course, us 90-second guys, sometimes I'm just 90 seconds, it seemed like a good idea at the start, but then I'm just really hungry, and the clock's hitting, 85 seconds, and I'm just like, I can't wait that last 5 seconds. And I pull open the door. Okay. So it turns out that, of course, microwaves are dangerous. You should not be exposing yourself to microwaves. And the microwave oven is set to shut off if you open the door early. But it's not instant, and there's about a millisecond delay between when you open the door and when the microwaves shut off. And so Emily Petrov was doing experiments, and it turned out there was a microwave oven downstairs at the Parkes telescope. So I should explain about Parkes if I back up. Parkes is unusual in that here's the dish. Normally the control room is like, a mile over there, but the control room is actually underneath the telescope. And so there was a microwave oven inside the control room. Never really a good idea. And people were heating up their dinners while they were looking for fast radio bursts and going, oh, I can't wait that 5 more seconds, and pulling open the door. And that produces this strange signal where the microwaves leak out, and for various reasons, the high frequency waves escape from the microwave a fraction of a second before the low frequency waves. And so it turns out that all these fast radio bursts that Parkes was detecting was just people who couldn't wait for the microwave to go ding and were pulling the microwave open early. And of course, lunchtime is an important time, and so you can see that people were, the peak is right at lunchtime. A little peak, you can actually see the secondary peak here at dinner time, and I don't know what people are doing at 7 a.m., maybe heating up their coffee or something. Okay, so she showed that a lot of these fast radio bursts were actually microwave ovens. At this point, we're thinking, oh, well, that was fun. But it turns out that the original fast radio burst, the Lorimer burst, could not be explained by a microwave oven. No one was using the microwave oven at that time. And then finally, after years of looking, people started finding these fast radio bursts with other telescopes that did not have microwave ovens in the control room. So a lot of them were fake, but a lot of them are real. The rate really is, it's actually now about 1 every 2 minutes, so getting rid of the microwave ovens ones knocked the rates down a bit. But after a bit of a scare, we discovered these were real things. And if you go to the Parkes Radio Telescope now, there is no longer a microwave oven in the control room, which in hindsight seems like it was a really stupid idea from the start, but we do not have a microwave oven in the control room anymore. And so fast radio bursts, despite a scare, are a real thing, and many telescopes now have found them. And so here are some examples, and they're all different. You might say, well, hang on, why aren't these ones all curved with the high frequencies arriving first and the low frequencies arriving last? Well, they are. It's just that now when we find them, we measure that curve, and we take it out of the data, and so now they always look beautifully straight. And this number here that's written here is telling you how much stuff the fast radio bursts have come through. So at this point, we had about 20 real fast radio bursts. And people had no idea. Lots of clever people started guessing what they were. And we very quickly got into a situation where we had more theories than we had bursts. There were like 30 or 40 different theories. And some of them were sort of not too exotic, things like just some star exploding. Others involved sort of semi-exotic things like 2 neutron stars smashing into each other. And some were very exotic indeed, like cosmic strings. And no one really knew. Like all of these possibilities were plausible. And not only that, you don't just have to pick one of them. Maybe all of these different things are producing fast radio bursts, and fast radio bursts are actually a whole bunch of different things in the sky. So the problem why we didn't know is because no one quite knew where the fast radio bursts were happening on the sky. So when the Parkes Radio Telescope or another radio telescope sees a fast radio burst, these big dishes actually have really blurry vision. So when they see a fast radio burst, the best they can do is say, oh, it was over there somewhere. And so if you now point a traditional optical telescope at where a fast radio burst happens, it doesn't really narrow things down much. So this is sort of a typical result. The radio telescope says, we found a fast radio burst, and you would love to know where it's coming from or what its environment is, or maybe see it in another wavelength. And the radio astronomers say, well, it's somewhere in here. And you can see that there's a lot of things in here. Most of these smudges are not stars. They're actually whole galaxies, each with hundreds of billions of stars. And so all you can say is, well, it's got to be one of these galaxies. And that's not super useful. You really need to know the location much better. And so this is a problem. The only way to find these fast radio bursts is with these big dishes, but their vision is always blurry. And then if you tell someone where to look, there's just no way to fix it. And so we were stuck for a couple of years until this very exciting breakthrough. And that, as I said, these fast radio bursts flash, and then they're never seen again. But there were heroic efforts, and the 10th anniversary of this is just coming up, and we're actually going to have a conference to celebrate this, because this was a giant breakthrough. We finally found a fast radio burst that repeated. So firstly, this was a big deal because some of these theories, just by definition, say they should not repeat. If a fast radio burst is being produced by a star blowing itself to bits, or by 2 neutron stars colliding, then that really should only ever happen at a given place once. Once they've blown themselves to bits, that's it. You're going to get a big flash, but nothing again. And same with evaporation of something, like once the object's evaporated, it's gone. And so immediately, by the fact that they found a repeating one, a lot of these theories seem to be wrong. So let me explain to you what's going on here. This is a graph versus time starting in 2017 and then going all the way through to 2019. And the yellow gold star shows when the fast radio burst flash happened. So there's one here, and then there's all these different telescopes going back and hoping it's going to repeat. Nothing, nothing, nothing. 2017, nothing. All the way through 2018, nothing. Very frustrating. And at this point, you can see that some of the other telescopes are given up because the director of the telescope is saying, don't waste my time. This is never going to repeat. No one's ever seen one of them repeat. But this telescope in Germany kept going, and in November, it finally saw this object repeat again. and then in August the next year it repeated again, and in September. So this is very exciting because it meant we now knew in advance that something was going to happen somewhere over there roughly. So now you could take a different type of radio telescope, an array, and so this is the Very Large Array in New Mexico, the VLA, and so this has much, much sharper vision, but it only has a tiny, tiny field of view. So you could never find a fast radio burst from scratch with this telescope. It just doesn't see a big enough patch of the sky. But if you know roughly where to look, you can point this telescope and just sit there and wait for one to happen. And then when it goes off, gotcha, I know exactly where you are now. So this was a heroic effort that took years and years and lots of time just staring at nothing. But now that we knew that this one repeated maybe about once a year, they stared and stared and stared. And finally, it went off while this array was looking at it, and they were able to nail the position of the first localized fast radio burst. And so the prediction, we knew these things come from billions of light years away. We're guessing they probably don't happen in intergalactic space just in the middle of nowhere. They're probably, given these objects are only 200 miles across, they're probably something that's inside a galaxy. And so we were really expecting, once we knew exactly where to look, that if you could pinpoint this object, it would be exactly on a galaxy. It wouldn't be in a blank spot, it would be like right here or right here. And lots of people were saying, well, most galaxies in the universe look like our Milky Way. So I bet you it's a galaxy like the Milky Way. And to our surprise, it was not in it wasn't a galaxy, so that was a bit of a relief. But it was a super ratty, pathetic little smudge of a galaxy called a dwarf galaxy. A galaxy that looked very different from the Milky Way. And so that was a huge surprise and spawned all sorts of new theories about what fast radio bursts must be. But this was the only one that repeated. There were only about 20 known, and this was the only one that repeated, and so this was the only one they could localize. So some people were saying, hold your horses. We don't know if the other 19 repeat, so maybe they're different. And we also don't know where the other 19 are. Maybe they're not in galaxies like this. So everyone was sort of stuck. We had detailed information about one, and it was quite strange. It repeated, and it was in a weird galaxy. And about the other 19, we sort of knew nothing at all. So how are we going to make more progress? Well, I am part of a team that built a new type of radio telescope that was supposed to solve this problem. And so this telescope is called CHIME. It's in Canada, in the Okanagan region of British Columbia, which is an incredibly beautiful part of the world. It has no microwave ovens anywhere near it. And what's more, we built it in a natural valley which shields out the signals from cell phones and other microwave ovens and TV stations and all the rest of it. And so here's a drone flyover. You can see the natural valley here. And here is the CHIME radio telescope. It looks like 4 skateboard ramps side by side. Each one is about 300 feet long and about 50 feet wide. And so it's, rather than a radio telescope that's sort of a dish, it's these particular 4 radio telescopes are cylinders. And just note these 3 white shipping containers off to the side here, because those are going to be important in a moment. So anyway, this is the CHIME radio telescope. It doesn't have any moving parts. It doesn't steer. It just points straight up all the time. And that makes it much, much cheaper than a telescope that has to have gears and motors and engines and all the rest of it. And it just sits there in the grass, pointing straight up all the time. So what that means is that it only sees a tiny little part of the sky. So this is a bit of a strange plot. This is this radio sky that I showed you earlier, but this is now the Earth rotating and looking up. So the shaded parts are the parts of the sky that you can't see from Canada. So these are the parts that are below the horizon. The light part is the sky that you can see at any one moment. And the red strip is the part of the sky looking straight up, this sort of arc overhead that the CHIME telescope sees at any one time. So you can see that on the one hand, CHIME only sees one little strip of the sky at any given moment. But on the other hand, if you wait 24 hours, the whole sky passes through our telescope. So over the course of one day, we have looked at every single spot on the sky that's visible from British Columbia. Just some more nice pictures of CHIME. Here's sort of a time lapse. This is an old telescope that's got nothing to do with CHIME, but this is a time lapse just showing it pointing straight up. This is a real photo. This is not sort of animated graphics or anything, just showing you the sky rotating overhead as CHIME points straight up. Yeah?
What direction
It's north-south. It aligns exactly north-south.
So if each of these tunnels is a single sensor, or you have a...
No, there's actually hundreds and hundreds of sensors. There's about 1,000 sensors along that strip.
Okay, so these things are aligned north to south.
That's right.
Okay.
Yeah. And as I mentioned, there is this shipping container off to the side. And the data rate from this telescope is incredible. It records about 10 terabytes per second, which is about the same as all the internet traffic in North America. Now, this is in the middle of nowhere. We do not have a big enough fiber optic cable to transmit all that data out there to some supercomputer. So we've actually had to build our supercomputers on site. So these 3 shipping containers are full of supercomputers. 10 terabytes a second comes into these, and then the process data, which is much less data, comes out through a normal internet connection. If you go into so these supercomputers are running 24 hours a day. They are incredibly powerful computers. They get very hot, and it can get very hot out there in British Columbia. So we spend a lot of money on air conditioning. And so if you go into these shipping containers, you can't hear yourself think. That doesn't do justice to it. It's unbelievably loud inside. All you can hear is this screaming of all the fans trying to stop the supercomputers from overheating. And obviously, those shipping containers are very well insulated. If it rains, you really do not want water to get into the shipping containers. I think we get the idea. Whoops, I'm going backwards. So CHIME has a big field of view, as I said. So this is the problem with Parkes. The Parkes Radio Telescope has a tiny, tiny field of view. So you're pointing at a particular patch with Parkes, and you're waiting for a fast radio burst, and there's a fast radio burst going off somewhere in the sky every minute, and your chances of one going off in your field of view are really, really tiny, which is why it only found a few in a decade of looking. But with CHIME, we have this huge field of view. It's instead of a tiny little dot, it's actually a big swath of the whole sky. And what's more, we don't try and guess where the fast radio bursts are. We just keep pointing straight up. And we let the sky rotate underneath. Hopefully it's going to do that in a second. Here we go. And as you can see, sometimes you get a fast radio burst going off just as CHIME happens to be looking at it. So we turned on CHIME, and within a few months we found our first radio burst. And we got very excited when we found our first one. In hindsight, I don't know why we got excited at one, because now it's just boring. We find one about every 8 hours. So far, we have found about 6,000 fast radio bursts. Here is 300 of them. So this is just 5% of all the fast radio bursts that we have discovered. We have found something like 95% of all of the fast radio bursts ever discovered. That is, we've found 20 times more fast radio bursts than every other telescope on Earth put together. And so this has completely changed the game. So the first big discovery we made is that we found a second fast radio burst that repeated. As far as we can tell, the vast majority of them do not repeat. About 95% of them do not repeat. But we have found around 50, I'll come back to that graph in a moment, we've found about 50 that repeat. So here is sort of a graph of the whole sky showing you every known repeating fast radio burst. There's just a couple in the southern hemisphere. We can't see the southern hemisphere. These are ones that were just by luck found by other telescopes. And here are all the ones found by CHIME. So we've found about 45 or 50 repeating fast radio bursts. So that's by far a tiny, tiny fraction, but it's clear that that was not unique. Some of them repeat. And then just to put in perspective just how many were found, here's a graph of how many fast radio bursts were known over time. So we start off at sort of 1, and then there's a little blip here when we found 4 more. And on we go, and you can see where all the other telescopes are slowly increasing, and every other telescope put together has got to about 100. CHIME started in 2018, and you can see whoosh, and we've just been going up. This stopped at 2024. We're now past 6,000. So for those repeating ones, we've been able to do that trick again. When we find one with CHIME, we have that blurry vision. But now when there's a repeating one, we put one of these other telescopes on it, and we wait for it to happen again, and we can work out where they are. And so that means that we can figure out which galaxies they're in, and what's more, we can figure out what part of a galaxy they're in. So this one is in a nice spiral galaxy, and you can see it's not in the center, it's sort of out right near the edge. Here's another one where it's out right near the edge, and here's another one where it's somewhere towards the center. So unlike that first repeating one that we found, which was in that ratty dwarf galaxy, it turns out that that's not the dominant situation, and indeed that first one was just a bit of an anomaly, and that most of them are actually somewhere in a spiral arm of a normal galaxy. But note that this is only the repeating ones. For the non-repeating ones, it's very hard at the moment to work out where they actually occur because you only see them once, and you can't ever see them again and work out where they actually happened.
Just a quick question. So in terms of so you mentioned the decay of the frequency of time, right?
Yeah.
Do they all have the same length of time?
No. So they all have different delays. So they're all at different distances. The nearest ones have been only about 1 million light years away, and there are now ones we've found that are 10 billion light years away. So some quite local and some that are incredibly distant. That dispersion only gives you a rough estimate of the distance, but the other important thing once you do this trick is once you know which galaxy it's in, for a galaxy which has different properties from one of these, there are other ways of measuring their distances, like something called redshift that many of you have probably heard of. And so once you have its host galaxy, you can actually work out its distance quite precisely rather than just a rough estimate from the dispersion. So, all right, what are these objects? Well, for the repeating ones, the current theory, and we're not really sure yet, is that these objects are magnetars. So these are very exotic objects. These are neutron stars, so like the neutron stars that we see in our own galaxy, but much more violent and energetic. As the name suggests, these objects have unbelievably strong magnetic fields. The magnetic field on the surface of a magnetar is about 1 trillion times stronger than the magnetic field of the Earth. As far as we know, 1,000 trillion times stronger. I left out a factor of 1,000 there. 1,000 trillion times stronger than the magnetic field of the Earth. As far as we know, these are the strongest magnets in the universe. And magnetars have a lot of strange properties, and people have suggested, and the other important thing is they're very small. They're only about 20 miles across, so that matches the requirement that these things have to be small because we know that has to be true. And they also have enough energy to be able to produce a flash of radio waves that you could see from billions of light years away. So there's this sort of rough theory that you have some distant magnetar in some other galaxy, billions of light years away, and then something happens, we'll talk about what that might be in a moment, that gives off a bright flash, and 1 billion years later, that signal travels all the way through intergalactic space to Earth, and we see it. So people said, well, okay, that's an interesting idea, but there's a problem with that idea in that there are actually magnetars in our own Milky Way, and we've never seen one of them do this. If it did that, then we'd see a fast radio burst up close, and it would be unbelievably bright. It wouldn't just be like a bright flash, it would just completely overwhelm all our telescopes. And we've never seen that happen, so this theory is probably wrong. All right, well then along came April 28th, 2020, and CHIME was doing its thing. It was just looking straight up, and a known magnetar that at that moment was not in the field of view of CHIME, but at that particular moment was somewhere over here, gave off two incredibly bright bursts. So not just one, but two. So you can argue this is sort of a repeat, but they were 30 milliseconds apart. A bright one and then an even brighter one, one after the other. And so this is what we saw with CHIME, and we just happened to have another telescope running as well, not a very big telescope, and you can see that it wasn't a microwave oven or something because this telescope was on the other side of Canada, and it's fainter, but you can see that detected it too. And what's more, there was a little experiment going on at Caltech. They had a telescope called STARE that's a tiny little telescope. That's the whole telescope right there. And it was looking at the whole sky all at once. And they only really expected to be able to detect super bright things. This is the student who was working on it, Chris Pachanek. And there are actually 3 of these little STARE telescopes, one here, and one here, sort of spread around 2 in California and 1 in Utah. And those 3 little telescopes, after we put out our announcement that we'd just seen something bright, they went back and looked at their recordings and said, oh wow, we saw it too. And what's more, because they had 3 stations, they were able to triangulate it and work out where it came from, and it came from a known magnetar. So this object is in our own galaxy, so now we're looking at a much smaller part of the universe. So here's what our galaxy might look like as viewed from outside. Here's a location of the sun, and this is an object that we had known about for about 10 years called SGR 1935 plus 2154. It's known to be a magnetar, it's right there, and it gave off something that looked just like a fast radio burst. So you've got to say, well, all right, let's take SGR 1935 plus 2154, and let's put it 3 billion light years away. Would you actually see it? And the answer is no, but it's not so faint that you would have missed it by much. So let me explain this graph. These are all sorts of different bips and burps from the universe. This is how bright they are, and this is how far away they are. And here are all the different types of fast radio bursts, all at distances of millions and billions of light years. And here is this object up here. It's much, much closer. It's only 10,000 light years away, but it's also much, much brighter. And if you want to ask the question, well, how bright would it look if you moved it further away? You just have to slide down these diagonal lines that you can't really see. So if you move this thing further away, it would go down this line here, and it would be about here, which is nowhere near as bright as these fast radio bursts here, but there are fast radio bursts that you can see from 10 million or 100 million light years away that match this one. So the conclusion is that this wasn't a super bright fast radio burst. It would have been amongst the fainter ones, but absolutely this event that we saw in 2020 was bright enough that it would have looked like a fast radio burst if you put it far away enough. So at this point, people start to really suspect that maybe all fast radio bursts are just these magnetars giving off these flashes. And so the current perhaps idea of what's happening is that something happens to a magnetar that gives off an incredibly bright flash, and that's what a fast radio burst is. And there's two broad possibilities. One is that it's just simply some sort of starquake, that there's some sort of cracking of the crust. The crust is under enormous strain because of the huge magnetic fields. And when the crust cracks, just like an earthquake releases a lot of energy, this starquake releases a lot of energy, and it manifests itself as this radio flash. And the other is that for perhaps, again, something to do with the magnetic field, but we don't really understand why, that sometimes the magnetic field arrangement breaks pieces of the magnetar crust and flings them off out into space, and they sort of smash into each other and produce this glowing nebula. And that when new pieces fly out and crash into the existing nebula, that sort of creates a flare. Both involving a magnetar doing something very energetic, both a little bit hand-wavy, but seems to explain at least the repeating fast radio bursts. But it makes sense, just like California, you can have one earthquake and then a bit later you can have another one. This makes sense because you would expect this to repeat. The magnetar isn't destroying itself, it's just having a bit of a moment, and so you could expect these things to repeat. But that's clearly not the whole story, because we know that some FRBs repeat and some don't. So for example, this one that was first discovered on the 14th of January 2024, this one, we'd never seen it before, but on this date it turned on, and ever since then it's been bursting about 500 times an hour. So it's been going off every few seconds. So that seems like a very extreme object. But here's another one. This one has been stared at for 2 straight years, and it's only ever gone off once. So there's clearly something going on. Some of them never repeat, and some of them repeat all the time. And so that doesn't seem to be able to be explained just by these magnetars. What's more, here's one that we found with CHIME that repeats not just randomly like an earthquake, but very regularly. Here's a graph for just a few seconds, and you can see it goes boom, 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 like clockwork about every half a second. So that doesn't sound like an earthquake at all. That sounds more like a spinning neutron star. So that's weird. And then here's an even stranger one. This is one that repeats randomly, but what we call the activity window is very regular every 16 days. So here's a whole bunch of random bursts. It's just sort of flashing on and off randomly. Then it sort of stops for 16 days, and then it comes back on and sort of flashes randomly again, and then it stops and it comes on and it gets random again. Like, what is going on here? It's got the best of both worlds. It's both regular and it's random at the same time. So one speculation here is that maybe this is a magnetar orbiting some sort of gas cloud or something, every 16 days. And so the interaction with the gas cloud sort of lights it up and it starts flashing randomly. And then as it moves into its sort of elongated orbit, it sort of shuts down again. It gets weirder. Magnetars, we think we know how magnetars form. They form in very dense gas clouds right in the hearts of where all the action is going in galaxies. And so you expect them to sort of be sitting in spiral arms or towards the centers of galaxies. And when we look back at those locations here, they're all sort of roughly where there's something happening in a galaxy. So you can say, yeah, those could all be magnetars. But then CHIME found another one. And so this is one where, as I said, our vision's a bit blurry. And we didn't know exactly where it was. But because we knew it repeated, we could tell other telescopes to look at it. And things are very strange. Here's a very nearby galaxy to us, M81. And we knew there was a fast radio burst coming from somewhere around M81. And we knew that when we got the exact position, it would probably be like, here or here or here. And instead, it was there. And you're thinking, well, wait, maybe it's not in M81 at all. Maybe it's just a background object. But if you zoom in, that's the exact spot that marks what's called a globular cluster. This is a big ball of stars. We have these in our own Milky Way too. This is like a retirement home for stars. It's a really ancient group of very ancient, dead, dying stars that orbits in a big ball right around the galaxy. There's about a few hundred of these globular clusters around the Milky Way. You can see a few of them just as little fuzzy patches with your naked eye. And right here is a globular cluster orbiting M81, and there's a repeating fast radio burst in it. This is like walking to a retirement home, and you're looking through all the rooms, like, old person, old person, old person, and the next one there's a baby sitting in there. Like, it really shouldn't be there. We cannot explain how you can possibly have a repeating fast radio burst in a globular cluster. It just shouldn't be there. So we're a little bit flummoxed. One of the goals is to find more of these things. We are just turning on a new exciting stage of CHIME. So here's CHIME. We have built some baby chimes. We've built 3 of them. One sort of halfway between CHIME and Vancouver. One at Hat Creek up near Redding, California. And one in Green Bank in West Virginia. And so we now have these baby chimes. And if you link them all up electronically, you're basically simulating one giant chime that's thousands of miles across. And what that means is that CHIME doesn't have blurry vision anymore. Now CHIME has eagle-eye vision much better than almost any other telescope on Earth. So just in the last month, we've started collecting data. And now when we detect a fast radio burst with CHIME, we don't get to say, oh, it's over there somewhere. But we can localize it to a circle that's like 100 times smaller than that green circle. So we instantly know not just which galaxy it's in, but exactly not just which street of the neighborhood it's in, and not just which house it's in, but which part of which room the fast radio burst is actually sitting in. And that's really going to be vital to figuring out just what is going on. So I'm very excited about that. I want to finish off just by reflecting about why I became an astronomer. When I was a kid, I was super annoying and drove my parents crazy and asked them lots and lots of questions. And so they shut me up by giving me books. And I love reading books because books had answers. So a book on volcanoes told me how volcanoes work. And a book on cars told me how cars work. But then they made a mistake of buying me a book on astronomy. And this is the book they got me. And I still have this book. And instead of telling me how everything worked, this book said, we have no idea what's going on. And I thought, oh my goodness, like I can ask questions for the rest of my life and I'm never going to run out of questions to ask. And at that moment, when I was about 4 or 5 years old, I had decided I want to become an astronomer. And I can sort of prove that I never wavered from that because about 5 years later, I went to the local county fair. And if you go to the county fair, there's someone sitting there saying, I'll draw a cartoon of you for like $5 or whatever. So I begged my parents and I sat down in front of the artist and they said, all right, what do you want to be when you grow up? And I'm sure they were thinking firefighter or airline pilot. And I said, well, I want to be an astronomer. And so here I am. I look exactly the same. My telescopes are a bit bigger now, but here I am at about the age of 10, drawn as an astronomer. And so it was this idea of there being questions that nobody knew the answers to that attracted me. But the amazing thing is, if I go back and read this sort of 40 or 50-year-old book now, it held these big mysteries and said we have no idea what these things are. The big mysteries are in this book. We know the answers to all those things now. They're just in textbooks. They're not mysteries anymore. For example, when this book was written, no one knew what these weird objects that we were finding on the sky were. There were all sorts of weird speculations, but as I've told you, we now know that they're powered by supermassive black holes. When this book was written, we knew the universe was expanding, and the big question of the day was that we didn't know the answer to is, we knew that the universe was expanding. We presumed that it had to be slowing down in its expansion. And the big question is, will it slow down gradually, or will it slow down so much that it will start collapsing in on itself again? And so that was the big question. Will it expand forever, or will it collapse in on itself? Well, now we know that not both of those things are wrong, that because of something we don't understand called dark energy, the universe is actually accelerating and getting faster and faster. So those big mysteries of the 1970s and 1980s have now been answered. So it's exciting that we have a genuine mystery. I love the fact that we don't know what's going on, but I guarantee that if you ask me to come back in 10 or 20 years, we will have all the answers. At the moment, this is a very exciting time, and I hope I have captured some of that excitement for you today. Thank you very much. And yeah, if we've got time, I'm happy to take some questions.
Probably trivial, but in the first plot you have of frequency versus time, the first radio burst, I noticed that the baseline before and after change. Is that just like a measurement artifact?
No, that's real. And so what happened was normally was that this burst was so bright compared to the things we're normally used to seeing that it saturated all the receivers and they basically lost their calibration. So you can see that the baseline changes afterwards because the telescope has actually forgotten what zero is supposed to be. So that normally doesn't happen. This burst was much, much brighter than the sorts of things we're used to looking at. Yeah?
I also noticed you're showing a specific frequency range. Is that really the beginning and end, or is that the same for all FRBs?
Well, as far as we know, the fast radio bursts sort of, have a huge range of frequencies. As far as we know, like the highest we've ever seen a fast radio burst is about 8,000 megahertz, and the lowest we've ever seen one is 100 megahertz. So we think they're intrinsically what we call very broadband phenomena. But there's technological limitations on how many megahertz you can observe at once. And at the time, 25 years ago, 300 megahertz was sort of considered the state of the art. And so this was considered quite a broad range. So that's the full data set that was recorded. These days we can sort of do more like 1,000 or 2,000 megahertz, but the fast radio burst signal extends over probably a much wider range. It's just that we don't have the technology to observe the full range in one gulp. Yeah, over there.
Question, it's generating a lot of energy. Is there any conversion to how much mass is being converted to energy? And can it be picked up by some sort of gravitational interferometer?
So we don't think that this is directly converting mass into energy. We think that this is converting perhaps magnetic energy into kinetic energy. You can work out how much gravitational wave distortion this produces, and it's a very small number. People have looked, because you might get lucky, but if you actually do the calculations, you really don't expect to see anything with current telescopes. Yeah.
Is there any reason why you only see this in radio? Why wouldn't you also see an optical or infrared flash at the same time?
Yes, so that's a great question. So people have all these different theories, and some of them say that there should be an optical or an X-ray or an ultraviolet flash at the same time, and others say that there shouldn't be. So if you could see or know if there was an optical flash, you could distinguish between theories. But can you see the problem? There's this dispersion effect, right? The high frequencies arrive first, and the low frequencies arrive last. Radio waves are the lowest frequency of all. So by the time you know that the radio signal has hit you, the optical and X-rays have long gone. So you cannot trigger, based on a radio event, to find the optical. Now for a repeater, you can. If you know an object repeats, then you can point an optical telescope at it. Well, first you have to find the exact location. And then once you have the exact location, you can now point an optical telescope at it and wait. And if the radio people tell you that there was a burst, then you can look at your data from 20 seconds before and see what happened. So for a couple of bursts, we have done that in the optical and in the X-rays. And so we have been pointing at the telescope, at the burst, at exactly the right moment where the optical light or the X-ray light should have arrived. And so far, for every one of them, we have seen nothing. We've actually tried to get cleverer, because what you can do is, if say the burst repeats 10 times, if you record the optical light at the right time for all 10, you can take those and stack them all on top of each other and average them together to see if there's like a really faint optical light. So we've done that too, thinking, aha, we're going to get you. And there's been nothing there either. So far to this day, except for that one that happened in our own backyard, in our own galaxy, we have never seen a fast radio burst in any other wavelength except in radio waves. The exception is this one that happened on April 28, 2020. This one, which is much, much closer, we did see X-rays and gamma rays from this one as well. So that leads us to think that if the ones that are happening in distant galaxies are just like this one, then we surely will see X-rays and gamma rays from them. But we just either have gotten unlucky or they're different. We keep trying, and so far we haven't seen anything. So you're right, we should be seeing it, but it's a hard experiment. We have done it, and we haven't seen anything yet. Other questions? Yeah.
So, sorry, I'm an engineer. I can't help but ask questions about trying. So it has 4 different sort of parabolic antennas. What's the purpose of having the 4?
So there's 2 purposes. One is that 4 has 4 times as much sensitivity as 1, but by having 4 that are side by side, you can essentially now not only know that it happened in this red strip, but you can actually figure out where in that red strip it happened. And so we have about 1,000 pixels from north to the south, and we have 4 pixels from left to right, so about 4,000 pixels within that strip. And that allows us to sort of say that the burst happened, where is it? Somewhere in this relatively small circle. If we didn't have those multiple cylinders, then the circle that we had would be so much larger that even knowing that it repeated would not be good enough to allow us to follow it up and to localize it.
And this is why you're excited about having these smaller ones co-located a long way apart.
That's right. So now we can essentially, ideally you just like one giant chime covering the whole country. Might be a bit expensive, and you can imagine some logistical problems, but it turns out you don't need the whole area filled. The precision of your telescope just depends on the telescopes on the edges. So it's really about how far away that one is from that one, even though you don't have 1 billion chimes all the way in between them. You can't see as faint. If we had 1 billion chimes, we'd be able to see much, much fainter. So we can't see as faint as if you had a telescope covering the whole continent, but we have this incredible eagle-eye vision that you have as if you built a telescope that was the width of North America. Yep.
For that reason, what was the reason then to have Allen be one so close to the original one? Why not spread it on the other side?
So the reason why is sort of somewhat mundane is that no one's ever done this before. People have built telescopes that span the country before, but never a telescope that spans the country and only has 1 millisecond of data to do it. And so we were trying a lot of new things that were very challenging, and it's much easier to do it over 100 kilometers than over 1,000 kilometers. So when we asked for money from the Moore Foundation, like Gordon Moore, Moore's Law, Intel, they gave us money and said, well, this is very untested technology. Why don't you see if you can get it working over 100 kilometers first? And if that works, we'll give you money to build more of them. So that one worked, and then we built the others. And this also just provides a useful sort of check in that if there's results, that sometimes it's hard to be sure of your results over these very long distances, but this one, having a short distance, always allows us to check that everything's working okay. Yeah.
Regarding the repeating FRBs, have there been any correlations observed in terms of the interval repetition relative to the distance of the source?
Yeah, so people have looked for things like the distance of the source or the energy of the object or something like that, and so far we have not been able to find any pattern at all. The only pattern we've found, and we don't really understand this, is the repeating ones have a longer duration than the non-repeating ones. So if you go back to here, you can sort of see that this one here is sort of longer, it's sort of wider than, say, this one here. So what we've found is that the repeating ones are almost always long ones, and often they have complicated structure with more than one peak. and the non-repeating ones are almost always very short and sharp. And for that reason, we don't think, well, at least I don't think, some people disagree with me, but I don't think that the non-repeating ones are just repeating ones that don't repeat very often. They seem to be fundamentally different, and they do have a different shape to their pulse. And we don't know why. But they're probably just two different types of objects that both happen to be fast radio bursts. No other questions? Yep, last question, sir.
How many sensors do you have along the line?
I think there are, from memory, I think there's 256 along each one. So there's like 1,024 of them altogether. And so every one of those 1,024 is recording data 800 million times a second in 2 polarizations. And so if you add all that up, you get like 10 terabytes a second. Yeah. All right, well, I'll hand back to Larry.
Let's thank Dr. Gaensler again.
Thank you very much.